Hi students, welcome to my lectures on chemical engineering thermodynamics. In the previous lecture, before I request you to follow from the beginning because every lecture is connected. In the previous lecture, I have introduced the concept of azeotropes. The other words, it's constant boiling mixtures. In today's class, let us find out at what particular composition azeotrope will form. If it forms azeotrope, at what temperature and pressure conditions it is going to form. So this is what we have discussed in the earlier class. Azeotrope is such a mixture, even though you evaporate, it will form a same composition. That means if you have the X1 is 60% liquid of composition 1, and if you partially evaporate, in the vapor phase also, it will be 60% of composition 1. Okay, there is no separation that is going to happen. It occurs at certain temperature, pressure and some composition. Okay, it could be X1 or Y1. Let us find out what are the temperatures, pressures, compositions at which the azeotrope is going to form. As you know, the Raoult's law, modified Raoult's law and relative volatility we have discussed. Let us use the composition curve. Okay, please follow my last lecture also. From the composition curve, we can able to identify azeotrope is going to form. For example, YX graph looks this way. Okay, and the blue curve can be of this type, which is drawn on the top side, and blue curve of this type can also be possible. Okay, so though wherever this blue curve is meeting this diagonal line, okay, that is where exactly azeotrope is going to form. In this case, the azeotrope is forming at this point. On the left hand side, if you remember the relative volatility, okay, based on this relative volatility, we can able to identify at where exactly azeotrope is going to form. Imagine, let us take this first graph. On the left hand side to this point, the curve is above this black line. That means the relative volatility on the left hand side, that means the blue curve, always the relative volatility will be greater than 1 if it is above this black line. The relative volatility will be less than 1 if the curve is below the black line. That means before the azeotrope, that means exactly at this point, which is X1, Y1 azeotrope. On left hand side, the relative volatility will be greater than 1. On the right hand side, the relative volatility will be less than 1. Exactly at this point, the relative volatility will be equal to 1. So wherever the relative volatility equal to 1, azeotrope is going to form. That means at this particular composition, if you boil, that means if you try to evaporate, purification cannot happen. Similarly, if composition curve looks like this, imagine the blue curve. On the left hand side of this point, the blue curve is below the black line. That means the relative volatility will be less than 1. After this point, the blue curve is above the black line. That means relative volatility will be greater than 1. That means on the left hand side it will be less than 1. On the right hand side it will be greater than 1. That means both cases is possible. Only condition is on the left it should be either greater or less. On the right hand it should be opposite to what is the relative. If it is on the left hand, if it is greater than 1, the relative volatility on the right hand side will be less than 1. If on the left hand side the relative volatility is less than 1, to the right hand side the relative volatility should be greater than 1. If any one of these conditions is valid, then in between these two the azeotrope exists. So that is how we have to identify the azeotrope. So using this procedure, that means using the modified Raoult's law, we can able to meet these conditions, then we can form the azeotrope. Okay, relative volatility from here. Okay, gamma 1 P1 side by gamma 2 P2 side. Then at azeotropic composition, alpha 1 2 will be equal to 1. That means exactly at this point. So if it is equal to 1, then at this point gamma 1, gamma 2 azeotrope by gamma 1 azeotrope is equal to P2 saturated by P1 saturated. Okay, this is the equation we are going to use to find out this azeotropic composition X1 AZ and Y1 AZ. That means X1, Y1. At the azeotropic composition is represented by AZ. Okay. The conditions. You can see the graphical explanation has been written in this conditions. That means at X1 tends to 0, that means to the left hand side it is X1 equal to 0, to the right hand side it is X1 equal to 1. That means towards X1 equal to 0, the relative volatility should be greater than 1. Towards the X1 equal to 1, relative volatility should be less than 1. Okay, this is the first condition. Condition 2 is this one. As X1 tends to 0, the relative volatility should be less than 1. As X1 tends to 1, the relative volatility should be greater than 1. So any one of these conditions is meeting, then you can confirm the azeotrope is going to exist. If azeotrope is going to exist, then you using this equation you can able to find out the composition. Okay, let us use one example so to find out the azeotropic compositions, pressures and temperatures. There is find azeotropic composition X1 AZ or Y1 AZ and azeotropic pressure. That means at what pressure this azeotrope is going to form. So these two things, one is X1 AZ, Y1 AZ and pressure. Azeotropic pressure is represented by superscript AZ. Okay. Given methanol and methylacetate, these two form azeotrope. If these two form azeotrope, at what particular composition it will form azeotrope? Okay, that is what we are supposed to find out. Given temperature is 45, that means temperature is given at 45 degrees centigrade. Okay, we have to find out the pressure and composition. So P1 saturated and that Antoine equations to calculate P1 saturated and P2 saturated, one is methanol and two is methylacetate. So temperature is given and the other parameters are given. That means you have to find out this gamma 1 and gamma 2, right? Activity coefficients. So activity coefficients comes from excess Gibbs energy models, which we discuss at the later stage. So one such a model predicts the activity coefficients. So if you want to predict the activity coefficient, ln gamma 1 is equal to ax2 square. That means if you know the composition, you can calculate the gamma 1. Ln gamma 2 equal to ax1 square. That means if you know the x1, then you can able to calculate gamma 2. Okay, then A is a constant which can be calculated by 2.771 minus 0.00523 into T. So temperature is given, A can be calculated, P1 saturated can be calculated, P2 saturated can be calculated. That has been reported here. Then two limiting conditions, right? For x1 towards 0 and x1 towards 1, you have to calculate relative volatility. Okay, that means one should be greater than 0, one should be less than 0. These are the things we are supposed to find out, because before you attempt, you have to first find out whether azeotrope is going to exist or not. So if it meets these two, any one of these conditions, then azeotrope is going to form. Let us find out. As x1 tends to 0, okay, you have to find out gamma 1, gamma 2. That means on the left hand side, you have to find out what is gamma 1 and gamma 2. On the right hand side, you have to find out what is gamma 1 and gamma 2. That means at x1 equal to 0, ln gamma 1 equal to ax2 square. That is nothing but gamma 1 is nothing but exponent of a, because when x1 equal to 0, x2 equal to 1. So gamma 1 is equal to exponent of a. Then what is gamma 2? ax1 square. At x1 equal to 0, ln gamma 2 is equal to 0. Well, ln gamma 2 is equal to 0, gamma 2 equal to 1. That means on the one hand side, you know gamma 1 and gamma 2. Let us see when x1 towards 1, what is the gamma 1 and gamma 2? When x1 towards 1 is equal to ln gamma 2 equal to ax1 square. When x1 equal to 1, gamma 2 is equal to exponent of a. So ln gamma 1 equal to ax2 square. When x1 equal to 1, x2 equal to 0, binary system. So ln okay is equal to x2 equal to 0, which is this one equal to 1. Okay. Now relative volatility, gamma 1 2 at x1 towards 0, y1 by x1 by y2 by x2, which is gamma 1 p1 sat by gamma 2 p2 sat. So we know exponent of A, because we know A, then we can able to know exponent of A. So relative volatility when x1 towards 0 is 2.052. Similarly, relative volatility when x1 towards 1 is gamma 1 P1 sat by gamma 2 P2 sat. So these two are anyway given. So using this 0.224. That means relative volatility when x1 towards 0 is greater than 1. Relative volatility when x1 towards 0 is less than 1. That means 1 is greater than 1, 1 is less than 1. So this condition has met. That means in between 0 and 1, the azeotrope exists. So let us, using this equation, we can able to calculate at what particular composition of the liquid azeotrope is going to form. So ln gamma 1 azeotrope by gamma 2 azeotrope means P2 sat by P1 sat, which has come from this particular term. I know P2 sat by P1 sat 1.4747. If what is ln gamma 1 azeotrope by gamma 2 azeotrope 0.388. So I know ln gamma azeotrope by gamma 2 azeotrope because gamma 1, but if ln gamma 1 is equal to ax2 square, ln gamma 2 is equal to ax1 square. Then what is ln gamma 1 azeotrope is nothing but ax2 azeotrope square, ln gamma 2 azeotrope is nothing but ax1 azeotrope square. So if you 1 minus 2, if you do ln a minus ln b, ln a by b. So ln gamma 1 azeotrope by gamma 2 azeotrope is ax2 az square minus ax1 az square. So if you simplify, if you common out a, x2 square minus x1 square, okay, then you know a plus b into a minus b, you can divide this. So a x2 square minus x1 square is nothing but x2 plus x1 into x2 minus x1. So this is at any point of time x1 plus x2 equal to 1 because it's a binary mixture. So this particular term will be equal to 1. The remaining term x2 is nothing but 1 minus x1. Simple a into 1 minus x1 azeotrope by x1 azeotrope. So from that ln gamma 1 azeotrope by gamma 2 azeotrope nothing but a into 1 minus 2x1 azeotrope. Then I know the value of ln gamma 1 azeotrope by gamma 2 azeotrope 0.388, which I equate. Okay. From this I can able to find out gamma 1 az is 0.325. Okay. So using this procedure I have found out azeotrope exists. If azeotrope exists, what is the composition of azeotrope? That is 0.325. That means around this example around 0.328. That means at exactly x1 equal to 0.328, the curve is meeting at the diagonal line. Therefore gamma 1 azeotrope is nothing but y1 azeotrope because at azeotrope x1 equal to y1, you know. That means if you know azeotropic composition is that is x1 0.325, which is equal to the y1. So now we have found out the azeotropic compositions. Let us find out what is the azeotropic pressure. Azeotropic pressure can be calculated using the same formula. Y1 azeotrope by x1 azeotrope is nothing but gamma 1 into P1 sat by P. That means a modified Raoult's law we are using. Okay, we are using the modified Raoult's law formula for the case of azeotrope. So y1 azeotrope by x1 azeotrope is nothing but gamma 1 azeotrope by P1 saturated by P azeotrope, that is pressure condition. I know gamma x1 azeotrope is equal to y1 azeotrope. That means y1 by x1 is equal to 1. From that, pressure, azeotropic pressure is nothing but gamma 1 azeotrope by P1 saturated. So let us find out the gamma 1 azeotrope. I know from these conditions ln gamma 1 is equal to ax2 square. Therefore ln gamma 1 azeotrope is equal to ax2 square. Okay. Therefore gamma 1 azeotrope is exponent of ax2 azeotrope square. If I know x1, I can calculate x2, which is nothing but 1 minus x1. So if I put the numbers here, I know A can be calculated from this equation 1.107. So I know all the numbers here. If I substitute, I can able to calculate gamma 1 azeotrope is equal to 1.657. So if I know the gamma, I can able to calculate what azeotropic pressure is nothing but gamma 1 azeotrope into P1 sat. P1 saturate I already know 44.51. If that is the case, the azeotropic pressure here is 73.76. Okay. This is how you can able to estimate what is the azeotropic composition and azeotropic pressure. Now we have found out whether it's a high boiling azeotrope or low boiling azeotrope. How we can able to identify? Very easy. Example, the azeotropic pressure you have got is 73. Okay. What about pure boiling points of 1, which is methanol, is 44. Pure boiling point of methylacetate is 65. But you got a pressure which is higher than the both. That means on one side you have 44.51, which is pure boiling point, and boiling pressure is 44.51. On other side, the pure boiling pressure of methanol is 65.64. This is methanol and this is methylacetate. But the mixture will have the boiling pressure of higher than these both. That means somewhere around here at a composition of x1 equal to y1 equal to 0.325. That is, it is meeting the pressure of the azeotrope is higher than the both the pure boiling pressures of methanol and methylacetate. That means it is forming high pressure azeotrope. That means you can see this is how we can able to identify. So if you remember my last class, you can able to identify this. High pressure azeotrope is nothing but low temperature azeotrope. Okay, this is how we can able to identify the azeotropes, and this is a method to calculate azeotropic compositions. Thank you very much. We'll meet at the new lecture.